What's up, peoples? This video is intended to replace the lesson where I was going to introduce work and energy for you. And this first day of material is basically the entire topic on one day. No sugarcoating it, no like taking it a little bit at a time. It's the entire foundation for the topic. And then what you do is you basically just practice until you've developed those skills. So let's start with this. And these notes are also posted already in Classroom along with this, a link to this video. So we start with work being defined as force applied for a distance. Okay, literally FD cosine theta. The units are Newton meters, force times distance, and the units are actually joules. Now theta is the angle between the direction of the force and the direction the object is moving. As you can see here in this example, I've just like pulled some block with an applied force across the surface. There is friction, and so let's look at that. If we do the work done by the applied force, it's literally the applied force F, A, acting for a distance d, and the angle between those two is theta, so it's FD cosine theta. When it comes to the normal force, the normal acts up and the displacement is to the right. Those are 90 degrees to each other, hence FD cosine 90. And same with gravity acting down and the object moving a distance to the right. Those are both 90. So cosine of 90 is 0. And gravity and the normal do not do work. I promise you that gravity and the normal will never do work for any of the problems we do. And friction acts to the left while the displacement is to the right. The angle between left and right is 180. Therefore, and cosine 180 is -1. Therefore, friction does negative work. And it will always, I promise you, for us, it'll always do negative work. Always, always, always. So that's how you calculate work. It's just FD cosine theta. Friction, always negative. If there's an applied force, see if there's an angle. If not, it's probably in the same direction it's moving. Now, the next part, these are pictures actually this is a picture of last year's notes from the board. We derived a couple expressions. So I don't want to get too hung up on derivation because it's in a video and you'll probably pass out. But I can tell you that when you lift something, the minimum force necessary to do that is going to be the weight of the object, or mg. And if you lift it over a distance, you're doing work, but that distance is height. Now, work causes a change in energy. That is an important concept. Work causes a change in energy, and energy is the ability to do work. They're the same thing. They're both measured in joules. So you have gravitational potential energy. That's what we derived here. Excuse me. Potential energy due to gravity is based on height. So we need to define a height 0. And I'll show you that in an example problem coming up. But it's energy based on height. You'll see. Now, I derived, I don't want to get too much in this derivation, but I derived an expression for energy based on motion. That's called kinetic energy. Okay, and the expression for it is 1/2 mv squared, 1/2 mass times velocity squared. So this is energy based on motion. Like, is it moving? Because if so, there's a velocity. If no, then there's no kinetic energy. So that's the work and the two forms of energy we're going to be dealing with for a while. Then there's the work energy theorem. All right. Work causes a change in energy, which is why it's written as energy final minus energy initial. And I've added the initial energy over to the other side. And now I get initial energy plus any work done, or a change in energy, causes a change in energy that gives you a final energy. And if we separate each initial energy, we have two types. We have kinetic and potential. And our final energy is, ooh, look at that. Nobody said anything from last year. That's supposed to be an I. That's an I. That should say I, initial, right here. That's not a final, that's an initial. So you have the initial energies on one side, the finals on the other, and any work done in between. I want to remind you that kinetic energy is it moving, yes or no? And potential energy due to gravity is it above height 0, yes or no? This is the work energy theorem. It is everything. It is how we do every problem. You can't say, I don't know what to do first. You read the problem, and then you start with the work energy theorem. And that's basically what it is. So here's a basic problem. There's a calivator. I'm good. An elevator being lifted, causing its speed to increase from 2 to 5 meters per second over a distance of 8 meters. What is the work done by the cable? Okay, let's sketch this out. I always recommend drawing a picture for this. So here's the beginning of the story, where the elevator is moving up with initial velocity of 2 meters per second. Later over here, it's moving at 5 meters per second. And it has gone up a distance of 8 meters. All right, and we're trying to find the work done by the cable. I have to admit that normally we will just be asking, like, what is the force of the cable? But this problem is pretty generic and pretty basic. So, excuse me. Damn, COVID. Anyway, here's where you start. You write kinetic energy initial plus potential energy due to gravity initial plus work equals kinetic energy final plus potential energy due to gravity final. And here are the questions you ask. The whole point of this is just to cross out things you don't need. So you say, initially, is it moving, yes or no? And the answer is yes, it's moving at 2 meters per second. Pretty easy. So I'm going to leave it there. Initially, is this thing above height 0? Well, we haven't defined a height 0, but may I suggest the lowest part of the story every time? Height 0. So right now, it's at height 0. And remember that potential energy is mgh. If h is 0, there's no potential energy. Are there forces doing work? Yeah, there's a cable. It's applying a force. I think it says it up here, and I may have skipped it. Yeah, did I? I don't see it. All right, well, I could tell you that I know I said gravity and normal do not do work, but things like friction and cables and applied forces, they can do work. All right, is it moving in the, so is there anything doing work? Yes, there's a cable applying a force over a distance, changing its energy. Is there kinetic energy in the end? Yes. Or is it moving in the end? Yes. Is it above height 0 in the end? Yes. So after this, you just write the equation for each underneath, 1/2 mvi squared. Now the work done by the cable is going to be the force, actually it wants you to leave it as work. That's weird. All right, we'll leave it as work. And is it moving in the end? Yes, 1/2 mv final squared plus mgh final. And now you simply sub in your numbers. 1/2, 1,000 kilograms times 2 meters per second quantity squared plus the work done by the cable equals 1/2, 1,000 times 5 meters per second quantity squared plus mgh. So we have g is 9.8 and h is 8 meters. Now, these problems, I'm just going to let you know right now, you're going to be making so many mistakes, it's ridiculous. And you're not going to be able to find your mistake if you go right from this to an answer. So what I would prefer that you do is that you wrote down each section, like this is 2,000 joules. This is the work done by the cable. This is 12,500 joules. And that's going to be a lot here. This is going to be 78,400 joules. So do each section, I'm telling you, because these problems are going to get really difficult, and it'll allow us to better find your mistakes, because if you just go from this thing to an answer, we'll never figure out what you did. But it could be as simple as forgetting to square. It could be as simple as, losing a distance, something like that. So anyway, right now you can find the work done by the cable, and you get your answer, which I don't really care about, but I don't know what's going on. How you all doing? Minus 2,000. Oh my God. I hope this is right. 88,900. Is that the right answer? I have no idea. Is there an answer up here? Nope. We're going to have to trust it, or you can tell me if I made a math error. But that's it. That's like the most basic problem. Now, there's going to be another link to a better problem. Example number 1 that's on your homework packet. And we would normally do that in class, but I made a video for it, and it does a really good job of explaining the process. and how to use the work energy theorem, how to decide if there's kinetic or potential energies. So I'm really strongly suggesting that you watch that video. Please, please, please. Anyway, that's about it with the introduction to work and energy. I hope you were able to follow. Bye-bye.